Welcome to Quantum Curious, and today we are going to discuss a very miscellaneous topic in physics called the Heisenberg Uncertainty Principle. And you might have seen or heard about this, and this is uh, a very famous concept in modern physics. So you might have seen this kind of equation in some kind of T-shirt on the wall or on a poster, or even in the book of undergrad physics. So this is a very famous equation, and it is the official form of the Heisenberg uncertainty principle. And it simply states that we cannot measure the position and the momentum of the particle with absolute certainty simultaneously. So the precisions are limited by the quantity given by Planck's constant, that is the h bar. So many of the people might think that this is the limitation imposed by our detectors or measurement devices. But that is not the case. The nature is inherently uncertain and it does not allow us to measure it perfectly. So we will see that how this is the case and how our current concepts or current understanding of the nature explains this uncertainty principle. So there are two views about related to the uncertainty principle, and the first one is the epistemic one. So the epistemic one view is about the general common sense of the public that the devices are imperfect and we cannot measure the true nature of the reality or true nature of the universe perfectly. So there is nothing uncertain and imperfect about the true nature of the reality and the universe. So this view still advocated by many scientists today, and it was held by the great Einstein when there was a debate going between Bohr and him. So the next view is the ontological one. So the ontological view states that the nature is inherently uncertain, and this is not the case, or this is not the fault of our devices, but this is the true nature of reality. So ontological one view or perspective states that the particles does not have the actual velocities or position at the same before the measurement. So particles have number of velocities or number of possibilities of velocities and positions. So particles can be moving with less speed or high speed, but this view does not exist before the measurement process. So particle can exist in any point of space. So this kind of view does not exist before the measurement takes place. So this kind of perspective is quite weird, but it is well supported by many experimental results. So we are going to discuss that ontological one, the view that is as well accepted and well debated uh, throughout the scientific community. So let's start with the de Broglie hypothesis. So in 1920s, de Broglie hypothesis was given by his thesis, and that is the doctoral thesis. And he stated that everything has wave nature, and he called the wave nature, that is the matter wave of the particles, and the particles wave nature or wave matter wave has the wavelength that is the inversely proportional to the mass and its velocity. So the larger the mass, the smaller the wavelength, so and the smaller the mass, the larger the wavelength. So this is the inversely proportional between the matter wavelength and the object of and the mass of the object. So we know that electron has very small masses, so they have more prominent wave nature. So consider we have a particle, and it is described by many possibilities of momentum and position, and it can be described by the wave packet. So wave packet is a bunch of many waves, and each wave describes the momentum or the wavelength of the particle. So we know that before the measurement, particle can have many possibilities of wavelength or momentum, and it can present a, at any moment uh, in any point of space. So wave packet is a very good concept and very well representative of the microscopic objects. So we want to know the actual position of the particle. So we have to superimpose many different waves. So many superimposed wave will have different wavelength, and uh, they will cancel out each other because the superimposition of troughs of waves and the crust of waves. So we have at the end very localized wave packet, but now we have uh, we have a good precision of the position, but we have added many momenta or many wavelengths. So we will lose the precision of the momentum. So this is the uncertainty principle at its very best, and it is represented by the very basic concept of the wave packet. So the particle is actually a wave packet, and we do not know any any we do not know about the momentum and the position of the particle before the measurement. So now consider we want to know the momentum of the particle, but now the particle will have only one wavelength. Now it has a precise momentum, but we have lost the the precision in position and in the process, because now the wave packet will be extended to very far points of the space, and it has the vast possibilities of position. So wave packet tells us about the probability of the position and momentum of the particle. The smaller the wave packet, the precise the location of the particle. The larger the wave packet, the less precision in in the position of the particle. So this is the uncertainty principle at very best, and it can be explained or understood by the idea of the wave packet. So actually, the point particles are just the wave packets, and this is the very modern view of the particles in quantum mechanics. So this is the uncertainty principle, and the ontological view is prevailed by many experimental results. So it is the uh, inherent nature of the reality, and the uncertainty is inbuilt in the very fabric of nature. So this is not uh, uh, our fault. This is not our fault and our device's fault, but rather it is the inbuilt nature of our reality and the universe. So this is for today. I hope you have understood a little about the uncertainty principle.